So problem 2 on exam number 1 has you and a friend standing on a level field a distance r apart. So I like to start by drawing a figure. You and a friend standing a distance r apart, tossing a ball back and forth, and you're told that the ball reaches a maximum height of h. Now, the first question, A, is how long is the ball in the air during each throw? Okay, so what do we have? We have the height h, but you should realize that the time a ball is in the air, which is what you're asked for, depends only on h. Okay, how do you solve for that, though? If you look at the equations for constant acceleration applied in the y direction, let's just call this x and y. Y is equal to y naught plus v naught yt plus 1/2 at squared, where a is going to be the acceleration of gravity, negative g. Now, do we have enough information to solve for t here? We know the acceleration. We know the difference in height. Well, the difference in height from start to end is 0, but we don't know the original velocity. So it seems like you might have a problem, but you can be a little bit clever and say, well, let's just analyze half the motion. Let's just analyze this half. Because if you do that, the original velocity at the top of that will go to 0, just like a will go to negative g. So what we have now is that y minus y naught equals minus 1/2 gt squared. Okay. So this will let us solve for time, because we know that y minus y naught is negative h. Remember, y is where you end, y naught is where you start, so you end lower than you start. So we have minus h equals minus 1/2 gt squared, and that we can solve for the time. Okay, time will be equal to, we'll multiply, well, the negative signs will cancel, so we don't worry about those. And so multiply both sides by 2 over g, so we have 2h over g, and it's for t squared, so we need to take the square root. That's the time for half of the motion in the air, so what we really need is twice that for the throw up and the throw down. So the time that the ball is in the air, how long is the ball in the air, is 2 times the square root of 2h over g. And that's part A. Part B then is calculate the initial velocity with which the ball is thrown, although you could just as well calculate the final velocity with which it's caught, because you should realize those two have to be the same. Okay. So we can calculate the y component of the velocity now that we know how long it's in the air. We have the expression vy equals vy naught plus ay times time. Okay, we know the time in the air, we know the acceleration. If we analyze half the motion, again, then we know vy naught at the top of the motion, and we can solve this for y. So what do we have? We have 0. Okay. Oh, actually, we'll analyze the motion when you throw. Vy naught will be the velocity at which you throw it up. Vy is at the top, so vy equals 0 equals vy naught. And the acceleration is minus g. The time it's in the air is 2h, or not the time it's in the air, but the time for half the motion, again, is the square root of 2h over g. So this is vy naught minus the square root of 2gh, just simplifying because we have g divided by the square root of g. And we can solve this for vy naught equals square root of 2gh. And in terms of components, that's our half of our answer for the original velocity. Now, how about the x component? Well, v sub x is constant. And it's equal to the change in position, x component of the position, divided by the change in time. We're told the change in horizontal position is just r. The total time the ball's in the air is 2 times the square root of 2h over g. And we could simplify that if we want and write this as r over 2 times the square root of g over 2h. So that's the x component of the velocity, and that's all you need. You were told that you could answer this question in terms of components, which is what we've done, or in terms of magnitude and direction, and you could do that now that you have the components, just the square root of the sums of the squares, and theta equals the arc whose tangent is the y component of the velocity over the x component, but that's just a little bit more work that's not necessary. So we're done with this problem.